Hi, my name is Aashish Roy. Today, I'll be presenting the paper Controllable 3D Generative Adversarial Face Model via Disentangling Shape and Appearance. It's a joint work between Carnegie Mellon University and Meta. Photorealistic 3D face generation has sparked a lot of interest in the domain of computer graphics and computer vision, fueled by applications such as creating virtual avatars, face animation, expression transfer, and downstream tasks in computer vision such as 3D face reconstruction. Mainly there are two approaches to generate 3D faces, computer graphics or machine learning algorithms. They both have their own set of advantages and disadvantages. Computer graphics can provide control over expressions, lighting, skin texture, camera position, etc. However, they necessitate a significant amount of artistic labor, which is both time-consuming and costly. Machine learning algorithms, on the other hand, can generate photorealistic models with natural image statistics useful for many applications. However, they require a large amount of data and doesn't capture subtle expressions, skin tone, lighting, etc. In this paper, we propose a new 3D face generative model that independently generates mesh and appearance, that is texture. This model can provide granular control over expressions by decoupling identity and expressions of a face. We simply used a pair of supervised auto-encoder and generative adversarial network to achieve this. In the first step, we train a supervised autoencoder which projects shapes into two low-dimensional embedding subspaces, one for identity and other for expression. The assay contains true encoders that share no parameters, allowing us to decouple and disentangle the representation of the identity and expression factors. However, it uses the same decoder to preserve the correlation between the identity and expression factors while reconstructing the mesh. The assay uses the classification laws on identity expression classes as a supervision signal. This supervision separates classes of expression identities and brings similar expressions and identity factors together in the embedding spaces. In the second step, we leverage a conditioned GAN to sample from the SAE's latent space. Similar to SAE, it uses two separate generators for identity and expressions, and one discriminator to classify real fake, identity class, and expression class. The pre-trained decoder can be used to generate a mesh from the latent space embedding. Similarly, we used a conditional GAN for texture generation. Specifically, we used a progressive GAN to sample textures from the same latent space as the mesh. A renderer can be used to combine mesh and texture to generate a photorealistic image. Here are some of the results synthesized using our pipeline. As you can see, we can generate different expressions for the same identity and vice versa. We can also provide granular control over different expressions, as can be seen in the figure. Similarly, we can synthesize textures corresponding to the identity and expressions and have granular control in UV domain as well. Here are some of the rendered results synthesized using our pipeline. As you can see, we can very nicely control expressions while preserving the identity. Thank you for listening me. For more details, visit our project page.